So what's the big difference? It's still attracted, rubbed, unrubbed. Similar to the magnetic effect, right? Come back.
Well, they're not metal.
Is it touching the table? The difference is, it's not ferromagnetic. This is a piece of wood, right?
It still has charges.
It still, oh, right, it still has charges, but we believe there's, oh, okay, so this is a slightly different effect, isn't it? But it still has charges. It's hilarious to do a banana hanging. They just walk in and you have a banana hanging from a string, and you do this and it follows around. You know, it just doesn't matter what it is. It's going to be, it does not matter what it is. If it's matter, it's made of charge. And so what have I done? I'm going to just talk about it, right? I'm going to say that I induced, this time, I induced an electric field. So here's the 2x4. And if it's an uncharged, what is it to be charged? What is it to be uncharged? It's a huge discussion. This is a work of Franklin and some others. But to be uncharged is not to be without charge. And when Franklin did his work, he said, how many types of charge are there? I think there's only one. And he named it fulvium. I don't know why. Fulvium. But he, you know, so he could say there's charge or there's an absence of charge. And in that way, he's kind of right. But what we know now is that uncharged is equal amounts of both. But what we also know is that true positive charges exist in the nucleus. We're not doing nuclear reactions here. We're just dealing with electrostatics. And so what we're really doing is moving around only the negatives. And if I take this negative and bring it up here, I've got excess negatives on one side, right? And by that lack of negatives, I now have a positive. So here's what happens. I take an object that's neutral, and I take an object that's charged, like the gray rod that I rubbed. And so we believe, I'm not going to dig it out of the bag, that in this universe there's a fixed amount of charge, another conservation law, conservation of charge, and that I can take charge and move it from one place to the other, but this is not the act of creating charge.
Yeah,
okay?
We're replacing her.
I am moving it around, right? And that was a big deal in trying to figure this out. So here, if I have, let's say I put excess charge, I'm not drawing the positives, I'm only drawing the excess negatives. What surrounds this thing? A field, right? Now, as soon as I have this field and I put something in that field, the charges in that field respond. And so the negatives are going to hightail it out of there and all go back here. And so I only have, there's still positive. I'm not drawing everything, remember. And so I only have attraction for a rubbed and an unrubbed, just like magnetism. Okay? Now, there's some other really interesting things about moving charge around, and I tried it this morning, and I can't show it. But what I would do is say, normally, I would take 2 styrofoam cups and just take something like this, an unrubbed rod, and treat it like this, and just treat it in one area. Okay, I'm going to try to transfer charge. I'm going to see if I can move it around, because I can put it on here. I get this charged effect on here, and then what I want to do is have a charge detector. And the charge detector is really simple. It's a piece of aluminum foil that's hanging on a straw.
That's in the prism physics.
Is that in prisms? Because it's Robert Morse, M-O-R-S-E. He's excellent. And so if I take this and I put this in the field, it would respond, but today it's just not going to do it. Normally, it picks up a little charge and it swings way out. But if I take it over here, it doesn't. In other words, I can put charge on here, I can move it around, but it stays where I put it. If instead I do this, and I put charge on there, because I try to do it in the order that Franklin did. Okay, I try to present it in that same order so they can see it's a human process. Otherwise, they think electricity just comes out of a box somewhere. Oh, I hear a little bit. Are you listening? The snapping. I don't know. It's not going to be enough to counter gravity. But in the winter, easily does it. And then I bring it down here and it pops out just as much, and over here and it pops out just as much. So I can show the difference between an insulator. An insulator takes charge but keeps it there. That's it. It takes it where you put it. But a conductor takes it and spreads it out all over. Okay? So that's an important idea in every kind of electronic circuit we want to deal with, is this idea of conductors and insulators.
You could
So
use just a little piece of aluminum foil and that might be...
I could, but I don't have time to try it. But you're right, I used to try tinsel in the summer because it's so lightweight, but it's so variable. You know, if you just would all come in here and not breathe and not...
So when you, Nancy, you rubbed in the first one and then you touched this one. So you're inducing like the opposite charge? Like
No.
you have negatives there.
That's a good question. What makes charge move? That's a really good question. We're going to run out of time. Let's try that one. Teresa, will you help me?